crystal plasticity-based models and constitutive theories to describe martensitic reorientation and phase transformations in single crystal shape memory alloys. So the photos which I show you here is basically like some of the devices that are actually used shape memory alloys in their manufacturing. Yeah. So if you look at some of the photos, this is basically like a stent which is actually used in your body. And with regards to the conference matter, in fact, shape memory alloys has also a lot of place and use in optoelectronics devices. Yeah, it's like photodiodes and all that as well. So it's not so far away from what you guys, the focus of this conference. So I just wanted to link what I'm trying to do with the main focus of the conference, which is optoelectronics as well. Yeah, so they have a lot of use in the photodiode industries, but the traditional applications are basically started off in the orthodontic wire technology. Yeah? So a lot of wire-based technologies, and also it's shape memory alloy springs, damping actuators, and also a lot of thermal switches as well. Yeah, in a lot of rocket space applications, yeah? in NASA and their jet engines. Yeah? And something which is probably more useful to most of us in a daily for daily life are basically wireframes, yeah, for your glasses. So if you actually buy an SMA-based wireframe, so if you actually step on it, if you just put it in hot water, you'll basically recover the shape. Yeah? So that's the beauty of materials made out of shape memory alloys. Right? So it remembers part of its shape if you don't deform it too much, that is. Yeah? So, okay, so without further ado, so this is the basic outline of my presentation. So I will briefly describe the microscopic phenomena of what is observed in shape memory alloys and its manifestation in the macroscopic sense. Yeah? So because whatever macroscopic behavior you see during your experiments has a microscopic manifestation. Okay? So, and then I will, just with one slide, I will briefly describe the basic governing variables to the mathematical equation. Yeah? So I won't go too much into detail with the mathematical model and the computational implementation. If you need more information regarding these models and the computational implementation, you're always like, you can refer to my papers, yeah, which have been published, and you can find them in Google Scholar and so on and so forth. And then I will briefly describe, like, where these models are being used yet. Yeah, so we will perform numerical simulations and basically final element simulations to actually predict the macroscopic response of these materials, yeah, under loads, yeah, under varying mechanical loads and thermal loads as well, yeah, because as you know, these materials are very sensitive to mechanical and thermal stimuli. So, and finally, I will conclude and talk a bit about future work. Yeah. So without further ado, so SMAs are basically still finding increased use as smart and functional materials and devices in industry. As I was mentioning previously, a lot of the recent applications are actually also in the optoelectronics industry, yeah, particularly as photodiodes, and they also are finding a lot of use as well in the civil structure industry, yeah, where they are used as dampers and basically as retrofitting devices, yeah, because they have a very good damping capacity. So in these industries, yeah. So they also have a lot of use as well, traditionally in the biomedical fields, where they actually used to make stents, orthodontic wires. Yeah, so stents basically you're put in your arteries in your heart or in your kidneys. So they're actually quite widely used as well. Yeah, and they're slowly trying to replace steel-based stents, yeah, which are not very ductile compared to shape memory stents, yeah, which is a bit much easier to deform. Yeah, and they also widely used in the MEMS field as well as in the micro actuators and temperature switches as well in IC engines and rocket engines. Yeah. So there are different types of shape memory alloys which are in existence. Yeah. So one of the earliest shape memory alloy which is basically discovered was in 1960s, yeah, by Naval Ordnance Lab. Yeah, and the composition is basically nickel titanium. Okay. Although there are lots of other different type of shape memory alloys made out of copper, indium thallium, even like recently like iron-based shape memory alloys as well, yeah, which is much cheaper. Yeah. So amongst all these different type of shape memory alloys which are in existence, the polycrystalline form nickel titanium is the most widely used shape memory alloy. Yeah? The reason for that is because it has ability for giving high actuation strains, and it also has an ability for high damping as well. Yeah, so that makes it very attractive for particular applications, like in terms of damping industries and actuation as basically actuators. Yeah. So some of the drawbacks include basically the amount of time it takes to perform actuation by temperature stimuli. Yeah. So that is why they have a lot of shape memory alloys which are basically made in wire form, so that the temperature actuation is faster. Yeah. In fact, a lot of people also use piezoelectric materials for actuation purposes, but unfortunately, the piezoelectric actuators have very small strains compared to shape memory alloys. Yeah? So in SMAs, the amount of actuation strains are about like an order of magnitude larger than the piezoelectric materials. Okay, so due to its ability to actually exist in different stable phases, which I'll explain shortly, it exhibits two technologically important types of behavior. One is called the superelastic behavior or the high temperature behavior, and the other technologically important behavior is called the shape memory effect or the low temperature behavior. Yeah? So we will describe the second effect more because that is the main focus of my talk, although I do touch a bit on the superelastic effect towards the end of my presentation. Yeah? So let's look at what is the shape memory effect in a global scale or in a macroscopic scale for an experiment which is done in a laboratory. Okay? So if you take a sample at low enough temperatures, which is a temperature which is below this martensitic finish temperature, yeah? It's a special temperature where below which, under the absence of stress, this material completely is in the martensitic phase. Yeah? So that's a low temperature phase and low symmetry. And this material basically has completely in the martensitic phase at the temperatures below theta mf. Okay, so you start off here, and when you deform it, you get some kind of elastic deformation. Yeah? So as you keep on pulling it, so you get some kind of seemingly permanent strain that is manifested in the body, yeah, as you keep going in. So you see a plateau, and you see some kind of a locking behavior as you go up towards this path C. Yeah. So when you unload it, you get a typical elastic reversal or reverse loading in elasticity. So, and when you have no stress in the body, in the sample, you have a permanent strain here in this case. Yeah. However, this permanent strain is not exactly permanent. If you increase the temperature of the sample below a certain temperature called the austenitic finish temperature, the martensitic phase becomes unstable and it wants to transform back into a more stable state. Okay. So when it transforms back to the austenitic phase, you get complete recovery from the martensitic phase to the austenitic phase. But what is more important is seemingly the permanent strain that was there, or the remnant strain that was there before at the low temperatures, is completely wiped out. Yeah? So it looks like as though nothing happened to the sample. Yeah? So it seemingly shows plastic deformation, but if you increase the temperature, this plastic strain disappears and you get a completely you get a complete state which is the same as the initial state. Yeah? So that's the beauty of the shape memory effect in the macroscopic sense. But what happens microscopically? Yeah? So from a microscopic sense, it's actually more useful to explain it through this diagram here. Okay, you start off with a single crystal austenitic phase which is stable at high temperatures. So as you cool it down, you basically form this martensitic phase, which are basically the stable phase at the low temperatures. Yeah, in this case, martensite forms in plates. Okay, so this is basically one plate here, and then it forms another plate here. And when this martensite forms under cooling, so they are basically also termed as self-accommodated martensitic phase. Yeah? So, and they are basically, these plates are split by interfaces. And if you look at the microstructure between the plates as well, like, within the plates, they are also split by different energetically equivalent configurations, which are called variants. Okay, so these variants, for example, this plate or system 1 here has variants 1 and 2, and for this plate J, it has variants 3 and 4. Yeah? So they are basically energetically equivalent, but oriented differently in three-dimensional space. That's all. Okay. And as you apply stress, the boundaries within the plates and interplates, they move as well. Yeah? And they are basically sensitive to the sign of stress. So if you stress it in direction 1, so the plates move in one direction. And if you stress it in the direction completely opposite of direction 1, so the interfaces will move in the opposite direction. That's all. Yeah. So it's very similar to dislocation slip, except that this is twinning. Yeah. So there's no dislocations here. There are basically dislocations within the variants, which we're not considering at the moment. But these are basically twin planes, which are basically mirror images of one plate to the other and one variant to the other. Okay. So as you deform it at temperature below the martensitic finish temperature and you let go the stress, you get a permanent deformation, which is completely recoverable when you increase the temperature. Yeah, theta dot when it's positive, that is when your temperature is increasing to above the special temperature here, which is the austenitic finish temperature, you completely recover all the plastic deformation that was basically imposed on it due to stress into its original space, which is occupied by the single crystal austenite. Yeah? So when you're doing modeling, basically you need to choose the representative volume element, and we choose a representative volume element of a single crystal austenite, basically a single crystal austenite, which when you cool down, you are able to form martensitic plates. Okay, so the representative volume element is basically this particular configuration here. Yeah? So it's the same space which is occupied by the single crystal austenite, but now it's in the low phase martensitic phase. Okay, so that is basically the microscopic description of the shape memory effect. And we need to distinguish different types of twinning that actually occurs, like, in this material. Okay, so there are basically two types of twinning. One which is called the habit plane variant or HPV reorientation, and one is the LCV or lattice correspondent variance detwinning. Okay, so to show it in a figure form, so this HPV reorientation refers to the conversion of one martensitic plate here to another, okay, through the motion of this boundary. Okay, that is the HPV reorientation. And the lattice correspondent detwinning is basically the conversion of one variant between the martensitic plate through the motion of these interfaces. Okay, so there are two different types of twinning that actually occurs here. Yeah, so and basically the phases are basically are mirror related. Okay, so that is the manifestation of twinning, or the description of twinning. Okay, so they are related through a transformation, yeah, from one space to another. Okay, so that is the distinguishing characteristic between HPV reorientation and LCV detwinning. So this problem is seemingly complicated, but we are actually able to make the problem in a more tractable manner to actually keep track of the HPV reorientation and decouple it from the LCV detwinning. Okay, so that is basically the name of the game that we need to keep track. So next, so what happens during, like, martensitic reorientation and detwinning in shape memory loss? Okay, so we take different samples, like, so we buy it off the like a catalog. So we tested two different types of samples. Okay, one in a rod fashion. Yeah, so you have like a nickel titanium in a polycrystalline form, which is in a rod configuration, and we also bought a crystalline sheet as well. Yeah, so this is basically manufactured by a rolling process. Yeah, so when you roll something, so you have preferential directions as well. Likewise, when you extrude something in a rod texture, you also get some preferential directions as well. Yeah? So you can clearly see we have done some laboratory tests, like, for nickel titanium rod here. Okay, so in this case, we look at a rod under tension and compression. Okay, so tension, you have a sample, you pull it, you pull it in tension. And we also perform a compression experiment where we cut a sample and we actually compress it, like, it's a cylindrical sample. Okay, so when you do this experiment, you actually clearly see some anisotropy in the or rather asymmetry in the response. Yeah, so you have initially, like, similar response up to about 2% strain. So, and as you keep on, like, pushing it or pulling it beyond 2% strain, you get a divergence of the stress strain response in tension and compression. Okay, you can clearly see that the tensile response is much more ductile and malleable compared to the compression. You get more of a locking response in the compression quite early on, about 2.5% strain or 2% strain. Okay, so clearly, like, the rod sample exhibits a tension compression asymmetry. So what happens in a sheet material? Okay, so if we do a typical, like, sheet tension experiment. Yeah, so you cut off samples, like, along the rolling direction of the sheet, and you have a transverse direction of the sheet, which is 90 degrees, like, orthogonal to the rolling direction in the in plane of the sheet, and we have something in between, which is 45 degrees as well. So we just show the rolling and transverse response here in stress strain response. So when you perform the deformation in tension, so you also clearly see a rolling and transverse asymmetry between the macroscopic stress strain responses. Yeah, so you can clearly see again the rolling direction is a bit more ductile and malleable, and you get more of a locking response in the transverse direction. Okay, so clearly it shows a rolling transverse asymmetry. Okay, so clearly the reorientation, because due to HPV reorientation and LCV detwinning, depends very strongly on two effects. Yeah? One is the initial martensitic microstructure. So whether you have a rod sheet, you have a rod material or a nickel titanium sheet, and also depends on the texture. Okay, and clearly, like, and the other thing that you notice is that twinning is a unidirectional phenomenon. Okay, so if you can twin easily in one direction, if you reverse the direction, you can clearly see an asymmetry. Yeah, so it is only preferential to one direction, unlike crystallographic slip, which actually is doesn't show any preferential direction. Yeah? So if we're doing it in tension and compression, the slip systems will be active. But in twinning, the twin systems can be active in tension, but sometimes it won't be active in compression. So that is the issue in twinning. Okay, so we have to take that into account into our mathematical model. Okay, so when you're developing a constitutive model or mathematical model, as I mentioned previously, you need to choose a representative volume element. So in this particular case, we've chosen a RVE, or representative volume element, of a space which is originally occupied by a single crystal austenite, but upon which cooling will comprise of martensite habit plane variants or LCB variants. Okay, and we've developed a single crystal constitutive model. In this case, we've actually have to take into account the crystallographic texture. In other words, crystallographic texture basically tells you how the crystals are actually oriented in space. Yeah? Okay, so since you have actually I've seen some of these XRD photos that you showed. So we basically have to do XRD to actually obtain how the crystals are oriented in space, and we have to take the spatial orientations of these single crystals in our calculations as well, yeah, for a polycrystalline body. Okay, and we've implemented the mathematical model into a finite element code. Yeah, so we've written our own special codes and used the Abacus FEM program as a solver. And we've actually performed a combined experimental, theoretical, and numerical investigation on how these materials deform and undergo shape memory effect. Yeah? So to the best of my knowledge, this was one of the first works that actually sort of encompassed all three types of analysis, yeah? Theoretical, computational, and experimental as well. Okay. So this is just a brief slide showing what are the governing variables in our mathematical model. So the most important thing is that you need to basically specify a potential energy, yeah, in this case. So in this case, we use the Helmholtz free energy potential. And from there, we need to use the Helmholtz free energy potential and use fundamental mechanical balance laws and thermodynamics laws as well, yeah, to derive the constitutive equations. Yeah. So for example, with regards to mechanical laws, you have to look at balance of linear momentum, balance of angular momentum, and if you're looking at the thermodynamics laws, we have to use the first law, second law, dissipation inequality. So all these tools we use to actually derive the constitutive equations. Okay, so and of course, finally, you also need to have some kind of description for the change of microstructure in the body due to twinning. Okay, so that is all obtained from crystallographic theory. Yeah? So which is called the phenomenological theory of martensitic transformation. Yeah? You can use geometry to actually calculate what the crystal lattice vectors and all that quite simply, using just basic mathematics. You can also use experimental analysis, but it's a bit more arduous to do the experimental investigation. So we've actually used mathematics to actually calculate what the the twin plane vectors are, the twin plane normals, the shear directions, and so on and so forth. Okay, so we've used the theory to do so. And then what we've done is, okay, for the first part of my presentation, I will briefly describe the experimental results and the computational results for a nickel titanium rod. Yeah, so for a polycrystalline rod. Okay, so we've purchased a rod of half an inch diameter. So and we made sure that it's martensitic at the room temperature. Okay, so we've also done some DSE measurements as well to find out what the critical temperatures are. Yeah? So the critical temperatures are the martensitic finish temperature, which is 316 Kelvin. So room temperature, at least in Malaysia, and I've done this work in Singapore, is 25 degrees Celsius. So we are good. Yeah, so it's clearly martensitic at room temperature, and the austenitic finish temperature is 363 Kelvin. Yeah, so it's a long way to go from room temperature. Okay, so we have machined out samples, yeah, for tension and compression. So basically, they are dog bone samples. Yeah, it's cylindrical in cross section, and also thin wall tubular torsion samples. Yeah, so we'll also perform, apart from just simple tension and compression, we'll also perform torsion type of simulations as well. Yeah, because we want to see what is the multi-axial loading characteristic, of this material, and whether our mathematical model and our computational framework is actually able to predict the behavior in the multi-axial stressing state. Yeah. Okay. So we've also performed these experiments under very low strain rates to keep the temperature conditions constant. Yeah. So we want an isothermal temperature condition for now. Okay. So we don't want to complicate matters. Yeah. So we just want to look at the mechanical response. Okay. So this is the crystallographic texture of the polycrystalline rod, as you can see. So you have to do some XRD, and these are the crystallographic planes. Yeah. So the austenitic phase is basically BCC, yeah, for nickel titanium. Yeah. So and the martensitic phase for nickel titanium is basically monoclinic. monoclinic. Okay, so it's very low symmetry, yeah, and it's high symmetry at the high temperature. So these are the crystallographic texture in the 111, 110, and 100 planes. Yeah? So you can do a XRT measurement, and this is the numerical. So the second column is basically the numerical, approximation to the actual experimental crystallographic texture. Okay, of course, you can take as many grains as you want in your calculations to make it more accurate to the experimental texture. But if you do that, you're actually increasing the amount of information in the computational framework, and the simulations will take longer. Yeah, so it's a balance of how many crystal orientations you need, and to match the experimental texture. Yeah, so if you can get away with as little as possible, the better. Yeah, to see how well it fits the experiments. Okay, so you don't want to burden the computational capabilities too much as well. So it's a balance between information and quickness of the computer simulations. Okay, so this is the experimental sample that we have here. This is the geometry. This is all in inches. Okay, so this is a dog bone sample. So we basically assume that a small part of the sample at the gate section, basically which is polycrystalline in nature, can be arranged randomly. So we have random orientation grains, which is basically each grain has a single crystal orientation from this crystallographic texture, yeah, from the XRD measurement. So this is the numerical representation of this experimental data. Okay, so each cube here is one finite element, which basically represents one single crystal austenite, which is now completely Martinsonic in phase. Okay, so they are basically oriented in space in a certain specific way. So, and then we perform the single crystal, the polycrystalline experiment. So this is the stress strain curve. So you can clearly see some elastic deformation here, and then some elastic plastic deformation. And as you keep on going, it sort of keeps going up. Yeah. So the reason why you get some kind of a hardening response is because when the twinning response is completed, so you get elastic deformation. Yeah. So basically this indicates that some grains have already completed the twinning process, but some are still basically twinning. So it's the competition between the elastic and elastic plastic deformation, which is what is causing the hardening response. Okay. So, and this is the fit of the mathematical model and the computational framework, and you can clearly see that the mathematical fit is quite good, yeah, with the experimental results. And we also performed a homogenized model of the polycrystalline, yeah, where we assume that basically all crystals are deforming the same way. So it's the computations are like an order of magnitude, actually 2 orders of magnitude faster. But of course, you have less information with the assumptions, and it's a constraint model. Yeah, so you will obtain an upper bound solution, yeah, for this case, yeah, where you assume that all crystals are basically undergoing the same deformation. Okay, so it's an assumption, but it makes the computations much faster, and you lose some accuracy, and you can clearly see so at some point you start losing the fitting of the experimental results, but by and large, the response is quite okay. So okay. Of course, we always want to go with the full FEM calculation, but it is slower. So we'll do an independent prediction in simple compression. Okay, so this is the compression experiment, and you can clearly see again you get some elastic response and some elastic plastic response, and the locking gets manifested much earlier compared to the tension experiment. Yeah? And you can clearly see here that the independent prediction of the model is quite good, actually. So, so our model is actually able to predict the premature locking in the experimental response, and the Taylor model is actually quite good as well in this case. So if you plot the full FEM results in tension and compression, so these are the simulations, you can clearly see that the tension, compression, and symmetry is actually well understood by the mathematical model and the numerical simulations. Okay, so it's quite a good job that we've done, at least in a simple tension and simple compression case. Okay, so let's try to make things more complicated. Okay, so let's try to do a multi-axial type of response. Okay, so with the same polycrystalline rod, so we cut up a tubular torsion sample. Okay, so machining the samples are quite expensive. Okay, so and you have a lot of wastages of material. So this is a tubular torsion sample. So with these dimensions, so what you do is you fix it at the grip sections which are here. So you fix the bottom part of the grip and the top part of the grip and the bottom part, and then you have a gauge section which is given here, which is undergoing a shear type of deformation. Yeah? You can also do tension as well, yeah, which what I will do later. Okay, so we form a tubular torsion type of experiment, and from there you will get a shear stress and a shear strain response. Okay, so this is a shear stress shear strain experimental response, and this is a pure prediction from the constitutive model. Yeah? So you can clearly see that the computational simulations are actually able to predict the experimental response to quite accurate accord, yeah, given the complexity of the deformation mechanisms and the microstructure in the material. So it also gets like, sort of captured by the constitutive model, and the homogenized model as well is able to predict the stress strain curve to good accord, albeit with slightly premature locking, but still the overall response is quite good as well. Yeah? So we are doing quite well in a multi-axial loading state. So let's make things more interesting now. Okay, so let's try to do a path change tension torsion. Okay, so we use the same sample as the tubular torsion sample, but what we do is we deform the sample in tension first. Okay, so we perform the axial deformation first to about a 3.5 to 4% strain, yeah, about 3.5% strain. So we deform it to 3.5% strain, and we fix the axial strain. Okay, so once the axial strain level is fixed, we perform a shear simulation at the same time. So so the axial strain is fixed, and you perform a shear simulation with the shear strain increasing with the fixed axial strain. Okay, so you'll get two type of responses here. Yeah, an axial response and a shear response as well. Okay. So this is the axial stress, axial strain response. So this is basically the same response, experimental response, as the response that I showed you previously, about 3 slides ago. And obviously, your model will be able to match this because we've actually used this experimental data to fit for the material parameters. Okay. But what is interesting is that if you once the axial strain is fixed and you perform the shear strain experiment, you can clearly see that so this will be an independent prediction. Okay, so the shear stress, shear strain response is also well predicted by the full FEM model and the homogenized Taylor model as well. Okay, so this is a pure prediction. But what is more interesting is you see a transient effect as the shear strain is increasing and the shear stress is increasing as well. The axial stress response actually reduces. Okay, so there's a drop in the axial stress response. There's a transient effect, which is actually predicted quite well by the model and the numerical simulations as well. Yeah? So we're quite happy that even the transient responses, not the main responses, are also predicted to be in good accord with the experimental response. Okay, so this is quite a complicated experiment, and our model is doing a good job so far. And finally, so we do a combined tension torsion experiment. Okay, so in this case, so what we're going to do is we're going to so for the same tubular torsion sample, we're gonna pull it axially and shear it at the same time. So it's like you're pulling it and shearing at the same time. Okay, so it's a combined tension torsion experiment. It's also called a proportional tension torsion experiment. Okay, so the previous one, this path change tension torsion, is a non-proportional path. Yeah? So in this case, this is a combined tension torsion experiment, which is a proportional path experiment where you actually obtain the axial stress, axial strain response and the shear stress, shear strain response concurrently as well. Yeah? So they are increasing together. And these are the experimental results for the axial stress, axial strain response and the shear stress, shear strain response. And you can clearly see that the mathematical model and the computational simulations are able to predict this to good accuracy. Yeah? So these are all independent validations of the mathematical framework and the computational implementation. Yeah? So it's not fitting anymore. This is a pure prediction of the response. And as I mentioned, despite the complexity of the material and the microstructure and the different type of twinning responses that you can actually get in this material, so it is doing quite a good job so far. Yeah. So let us see, maybe we got lucky with this particular rod sample. So let's see whether we are able to use the same mathematical model, of course, calibrate the different constants because we're going to look at a different material for a different type of textured material. Yeah? So we'll look at a sheet material in a second. So, but that is a true test. And finally, we've also done a prediction for an indentation response. Yeah? Because sometimes you want to look at a very complicated, like multi-axial loading path, and indentation is actually a good experimental response where you have a block of material and you have like a indenter. It could be a Berkovich indenter or conical indenter. We've taken a conical indenter and we've indented the sample, and this is the force displacement response from the indenter. And you can clearly see that the experimental response is actually quite well predicted by the polycrystalline simulations. Yeah? We've used the Taylor model in this case, okay, because the deformation here is basically non-homogeneous. So we have to use some kind of homogenized response at the Gauss point level or at the finite element level, okay. And we clearly see the effect of twinning here. So for example, if you suppress the information on twinning, that is, if you don't take into account the twin planes and the HPV reorientations and the detwinning planes, and if you do a pure elastic response, you can clearly see that it is completely over predicting the experimental response. Yeah? So it is important to take into account the crystallographic nature of the sample and that crystallographic nature of the twinning and HPV reorientations in your calculations to get an accurate description of the indentation response. Okay. So the second part of my talk is basically what we've was briefly describing earlier. Is we want to see whether we got lucky with the polycrystalline rod. Yeah? So we look at a different type of a textured shape memory alloy. So we look at a polycrystalline sheet material. Okay, so we've again purchased the polycrystalline sheets, but it turned out that we could only buy a sheet which is exhibiting superelastic response at room temperature. Yeah, where superelastic response is, I will show you the graph for it. It basically describes a complete reversible transformation at a certain temperature. Okay, in this case, like above room temperature. Okay. So now what we need to do is we need to make the material in the austenitic, in a fully martensite state. So we have to do these experiments now in a temperature chamber. Yeah. So we have to cool it with liquid nitrogen and do the experiments at a temperature lower than 298 K. And before doing so, we've also done a DRC experiment to check what the critical martensite temperatures are. So the martensite finish temperature is 207 Kelvin. So we have to basically cool down the temperature chamber to below that to ensure that the material is completely martensite state, yeah, in a completely martensite state. So, okay, so we've machined out samples like, along the rolling direction, the 45 direction and the transverse direction. Yeah. So this is a very standard experiment done by mechanical engineers to characterize anisotropy in a sheet. Okay, so this is dog bone samples, yeah, and they're basically machined in different directions, and we've actually tested it at 200 kelvins, like under very low strain rates. Okay, 200 kelvins is below theta MF, which is 207 kelvins, so it is completely in the martensitic phase. Okay, so then we also perform the measurement of the crystallographic texture at room temperature, and this is the numerical representation of the crystallographic texture. Okay, so we have the TD, which is the transverse direction of the sheet, and then RD is the rolling direction of the sheet. And this crystallographic texture is basically measured by putting it by actually sending the X-rays on the normal direction of the sheet. Okay, so this is looking at the normal direction of the sheet. Okay, you can clearly see that along the normal direction of the sheet, it is very strong 111 type texture. Okay, so it has a rolling texture along the 111 directions, but we are not testing along the normal direction. We are testing along the rolling direction and the transverse direction. Okay, so this is completely a different crystallographic texture. Okay, and this is the finite element representation of the material. Okay, so each element here basically represents one single crystal, which is originally austenitic, but now is fully martensitic. Okay, so the next graph here shows the experimental data for the sample which is cut along the 45-degree angle, which is basically in between the rolling direction and transverse direction along the plate of the sheet. Okay, so it's along this direction. So this is the experimental data, and this is the fit of the experimental data using our concentricity model. Okay, so we've used this experiment to determine the material constants in our mathematical model, and once we've already fit the material constants, we don't change it anymore. Okay, because we need to do independent predictions. Okay, so now this is basically the list of material parameters. So there's not that many actually. Of course, we've made a lot of assumptions, but we want to see even with the first cut assumptions, how far we can go by to predict the experimental response along the transverse direction and the rolling direction. Okay, so this is not too important. Okay, so this is the experimental response along the rolling direction. So we have that here. And then we have the experimental response in transverse direction. And you can clearly see that the mathematical model and the computational framework is actually able to predict these experimental responses along the two directions, the two testing directions to good accord actually. Okay, so quantitatively, they're actually quite good. And what is more important that is if you actually plot the numerical responses along the rolling and transverse directions, you can clearly see that the mathematical model is able to duplicate even the rolling transverse anisotropy in the material as well. Okay, so we are actually able to predict the tension, compression, and symmetry in the rod sample, and also the rolling transverse asymmetry in the sheet sample. Okay, so and what we clearly see here is basically along the for the sheet material, the transmission strains are higher along the rolling direction, and we're predicting that. And the stress levels for actuation is also higher in the transverse direction, and that is also predicted by our mathematical model. Okay, so since we have already done two textures, so we believe that the model can be actually extended to simulate the deformation response for any other texture as well. So that's the hope. Yeah, so we've done at least two textures. So we hope we can be able to do n textures. So we leave that exercise to other researchers. Yeah, so we don't want to be doing everything. So I was also at a phase of my career where actually I wanted to try something different. Yeah, so this was basically some of the last work I've done on shape memory alloys. Okay, so it's quite some time ago. Okay, so now finally we've come to the superelastic effect. Yeah, so what is the superelastic effect? Okay, so this is the effect which is actually manifested by shape memory alloys at temperatures above the austenitic finish temperature. And this is one example of an experiment under constant temperature. Okay, so you start off at point here, this initial state, it's completely austenitic, and as you can deform it, so you get some elastic behavior and then you get some kind of elastic plastic transformation, yeah, from a austenitic phase to a martenseric phase due to phase transformation. Okay, so and as you have phase transformation, you have a release of latent heat as well. Okay, so and when you have reverse loading, you get a reverse transformation from martensite to austenite phase, and you have the effect of latent heat, which is basically being absorbed. So if you touch the sample, it'll be cooler along the reverse loading cycle, and it'll be heated along the forward transformation. Okay, so when you release the stress, you completely recover your full state. So it looks like as though the material has not gone through any deformation, but actually it has some hysteresis, which is basically imparted, in the material. You get some dissipation because of the motion of austenite to martensite transformation, yeah, and release of latent heat as well, and absorption of latent heat. Yeah, so that is basically the superelastic effect. Yeah, so the shape memory effect is basically a combination of the detwinning and HPV orientation effect and a reverse transformation from the martenseric phase to the austenitic phase. Okay, and it is manifested by this experiment here. Okay, so this is the stress strain temperature diagram here, which you have here. Okay, so so we started off with the experiment at 45 degrees for the sample. So this was the previous experimental data. Yeah, so we have deformation intention, and once you let go the stress, you get a permanent strain here, about 6% strain, 6.5% strain. But what happens is, if you increase the temperature of the sample under zero stress, you get some kind of a coefficient of thermal expansion effects. And then when you reach a certain critical temperature, you get a complete reversal from the martenseric phase to the austenitic phase, and a complete recovery of the transformation strain. Okay, so that's actually predicted by the constitutive model as well. So you can clearly see this is one for the 45 degrees sample, and then you do the same thing, so don't worry about the material constants here. So so and you do the same thing for the rolling direction experiment and the transverse direction experiment as well. Yeah, okay, you can clearly see that whenever you reach a certain critical temperature, you get a complete wiping out of the remnant strain, yeah, which is about 6%, which is quite large. Okay, so and it happens about the same time when the experiments actually show that. Okay, so what happens here? So the conjecture is that we believe that the martenseric phase has completely transformed into the austenitic phase. Okay, so we want to see whether that is true. So we show the results, the final element simulation results. So, and lo and behold, actually that does happen. Yeah, so this is the state of the polycrystalline material in the low temperature state. Yeah, 200 kelvins is completely martenseric. So as if you increase the temperature to about 285 kelvins, you get a complete reversal of phase from the martenseric phase to the austenitic phase, and that's actually predicted by the mathematical model. Yeah, and this is actually what happens in the experiments as well. And our computational simulation is actually able to predict the experimental effect to quite good accord. Yeah, so that is basically the so we've come to the conclusion of our presentation. Yeah, so what we have done basically, so what we have achieved in this project is basically we've actually developed a microstructure informed mathematical model, yeah, or a crystal plasticity based constitution theory, which takes into account the large changes of the large deformation effect due to twinning and HPV orientation in this material. Okay, because if we're looking at the samples in a single crystal state, the twinning shears can go up to about 28%. Okay, and in fact, they've also discovered new shape memory alloys that can go larger as well. So you need a finite deformation type theory where you have to worry about Galilean frame invariance and so on and so forth. Okay, so these concepts which are quite familiar to physicists like you guys. So frame invariance and all of that. So we have developed a mathematical model to describe the martensitic twinning and reorientation in shape memory alloys. So we've actually implemented this into a computational framework, by writing our own codes, and implemented it into Abacus. So the mathematical model and its computational implementation is actually able to reproduce the stress and responses for experiments conducted on two different type of textured shape memory alloy. One in the rod state and one in the sheet state. And we are able to predict the macroscopic response quite well. In other words, the stress strain response and the stress temperature response. And finally, the experimental shape memory effect is also reproduced quite well by our theory and numerical simulations. Okay, so there's still a lot of work needs to be done on it. I think part of the future work, which I guess future researchers can actually do, is to actually include the dislocation slip within the twins itself. So as you keep on deforming it, to much larger strains, so you can get crystallographic slip. But what happens is that you lose the technological benefit of the shape memory effect, because once you introduce dislocations in the twins, it doesn't. The twin faces don't want to go back to its original shape. So that is why you don't want to deform it too large. So sufficiently large, but not too large, because you lose its technological relevance, for industry. So unless if you're going to look at a one-time actuation or something, then it's not a big problem. Like for example, if you're looking at a high temperature shape memory alloy switches, used in the IC engines, for rocket launch purposes, you actually use it for a one-time deployment. So then it doesn't matter. So you can go quite large, because after that you're not going to reuse it again. So you just chuck it, okay, or just let it float in space. So with that, I thank you so much once again for your kind attention.